Seattle. Huh? No, Alex is in Seattle.
Alex is in
Seattle. We're going for the conference. Who's called me? Who's called me? Boring?
Frustrating. Frustrating.
They said they're gonna patch it. Why is it frustrating? It's the same shit. But you don't really explore, right?
Well, I played the beta. Both games, Infinite Warfare and COD Remastered.
Yeah, I want
It's like paper helps, to be honest.
Really?
And ClickJaw uses there's some really huge advantage in ClickJaw. And
just go back to like Call of Duty 4.
I had to study for C++, and I was like,
I knew. I was like, shit, we have a test room. It's gonna release.
I didn't even play that much. I just got frustrated at the game. And the maps that were in the beta, people were camping their ass off. I was like, I ain't got time for this shit.
My Battlefield.
All right, so let's go ahead and jump in. So we're definitely going into homework 8 material today. That homework is already available. All the exam practice materials are available as well when you're ready for them. I posted not one but 2 back practice exams for your preparation. So basically, question back there? Richard, do you have a question? No? Okay. What we will be doing in homework number 8 is basically taking the tools that we learned in homework 7. What's the point of all this stuff? These adiabatic processes, isochoric, isobaric, and we're going to put them together. So this is where we take a look at things like car engines and refrigerators and figure out how they manipulate the properties of gases to actually do something useful for people. So we're going to start with the gasoline engine. This is something called the Otto cycle. This is basically, unless you drive a Prius or a Tesla or something like that, you probably used one to get here today, or maybe you walked, okay? So here's what this cycle is. Start with the PV diagram. And the cycle is 2 adiabatic and 2 isochoric. So what that means then, I guess let's go ahead and draw it. So I'll start somewhere. I guess I'll call that point A. And then the very first thing I'll do is an adiabatic compression. So adiabatic compression looks like something like this. It'll follow an adiabat. So remember that those lines are steeper than isotherms, so I have to make sure to note the fact that if this is my temperature isotherm for point A, this is on a different isotherm. This is temperature B. All right, so I've adiabatically compressed the gas, I've put work into it, and I've increased its temperature. Next up, I'm going to put even more energy into it, but as heat only, not as work. That's your isochoric. And you're going to rise up to temperature C. So that's my isochoric process. Then I'll go ahead and mark an isotherm off of this. This is my TC isotherm. Then I go ahead and I do an adiabatic expansion. So remember, when you're moving along an adiabat, those lines are steeper, so you're going to fall off, your temperature is going to drop. Energy goes out of the gas as work. So we wind up at point D, which again I'll mark off with an isotherm, temperature D. And then finally, to close the loop, we go from D back to A isochorically. So we do have enclosed area, that's the network. That is the network output of this engine when this cycle is undertaken once. So notice here that there's only two volumes that form the extremes of this. Basically, the volume goes back and forth between these two extremes. We might call them V1 and V2, but for purposes that will become apparent later, we want to express one as V and one as R times V. So we express one volume as a multiple of the other. So if the minimum volume we call V, the maximum volume is R times V. R gets a name, it's called the compression ratio. It's basically how many times bigger is the volume of the gas in its max than it is at its min. Okay? And I want to point out that because of this process being too adiabatic and too isochoric, that means that while it bounces back and forth between two distinct volume extremes, there's actually 4 temperatures involved, right? Each of the endpoints of the process occurs at 4 different temperatures. So you can think of kind of as like the extremes of this system are 2 different volumes and 4 different temperatures. Okay? So that's the gasoline engine cycle, right? So let me show you how this is actually implemented, okay? So I guess let me pull it up here. I'll give you a couple different ways to view it. So again, these are available for you to play around with. This one you might have to battle with a little bit more to get it to work because I think it's a Java. So here's what we have, okay? This right here is your chamber of gas, okay? And one of the walls is a piston, and that piston can be moved up and down to change the volume that the gas occupies. And the piston is actually attached to a crankshaft. So it turns, it can either put or take rotary motion away from the linear motion of the piston. What we have here are 2 valves. One valve is here, one valve is here. This is called the intake. This is where we get fresh gas. This is mostly air. Air we learned is diatomic. It does have some fuel in it, some gasoline, but we're going to neglect the gasoline that is a much more complex molecule with a lot more degrees of freedom, but it is mostly air, so we'll take it as diatomic. That's where we can intake fuel. And then, once we burn the fuel, this is the exhaust, okay? So, I've set this up in the order that I've just done the process. So we'll start with the adiabatic compression. So we'll move from here to here, okay? So let's take a look. That looks like this. Oh, that's a super small step. Let me not do that. Okay, so we're going to compress the gas, okay? Let me pause it right there. So we've compressed the gas, and we've heated it up, okay? So just like that bike pump effect, right? We've adiabatically smushed the gas into smaller speeds very rapidly. We've put work into the gas to raise its internal energy and temperature. Okay, next step. What we're going to do is we're going to increase the temperature even more, basically by putting in heat. Where does that come from?
Lighting up the gas.
The spark plug goes off, which creates a spark, and it combusts the fuel, and that combustion is going to release more heat, okay? So, here we go. Boom, okay? So, notice that this gas, indicate that the spark plug, which is right here, has ignited the gas. That has basically put more heat into the system, and since that combustion happened very rapidly, the gas doesn't really have much of a chance to change its volume. It's happening on a much faster time scale than the piston is moving. Okay, so that's called the ignition. Okay, so we had compressing the gas. That's called the compression stroke. This is called ignition, and now we're ready to make use of the fact that a bunch of gas just exploded in there. It's going to drive the piston down. This is called the power stroke. So it's going to push the piston down, and it's going to cause the crankshaft get work out of the gas goes into the crankshaft. So we had to put work in to compress it, but we get even more work out during the power stroke. That's where your net work comes from. So then we watch it, play through. Why is it stopped? It's
the red point jumped straight up again.
I know, but the animation won't work anymore.
Jeez.
I guess I'm not going to be able to pause it. So here's actually the power stroke right here. I didn't want to start there, so let me kind of let it go here for a second till I'm back at the beginning, and then we can talk through it as it goes. Unfortunately, I'm not going to be able to pause it because it's misbehaving. Okay, so here we go from the beginning. Here's the compression stroke. We're compressing the gas, and we're causing it to go to a higher temperature. Okay, so there's where we started. Then spark plug goes off. That's the ignition. Okay, here we go with the power stroke. That exploding gas drives it down. And now that the gas is expended, we got to get rid of it. So what we do is we take that, we expel the smoke, and we take in some fresh new mixture of unspent fuel. Now notice that's a whole extra trip up and down again. You got to expel the old burnt fuel and get the new in, but that's sort of happening kind of outside of the PV cycle, because basically you're just pushing spent warm exhaust out and pulling in new fresh stuff. And so what the net effect of that process is you start with a full chamber of warmer gas and end up with a cooler gas. Now, of course, it's literally just replacing what you had. It's pulling in fresh stuff after you've expelled the smoke. But the net effect of that is isochoric, right? The net effect of that is you wind up with a full cylinder full of cooler gas. Does that sort of make sense? So that whole extra, why did that stop? I don't know why this is misbehaving. Anyway, so that right there is the gasoline engine, what's going on. Let me give you another one. This works a little bit better. So this is actually a great website I found. It's called animatedengines.com. It basically shows you not only what's going on with the gas, but all the mechanical workings, and it has like 10 or 15 different engines that it has animations for. Okay? So this gives you a little bit more of a sense of how this all works. So let me pause it here. Okay, so here we are. We are just about to do the compression stroke. Okay, we've pulled in fresh air-fuel mixture, and we're just about to compress it adiabatically and increase the temperature. So here we go. There we go. Okay, and here I didn't pause it quite quickly enough. The spark plug has already gone off. So there is your ignition. Now, how did the spark plug know to go off right then? Well, it's just mechanically attached. This is tied to a circuit which is triggered at the right point in the cycle. So when this gear is attached to this gear, there's a little kind of flat spot on this thing where it actually triggers the spark to go off at the right time in the rotation. So if you want to get the timing of anything correctly, the whole idea is just make it mechanically tied to the position of the piston, right? So then we have your ignition. There's there's your ignition and now your power stroke. Okay? And now we have to push out the spent fuel. Now, how did this valve know to open? Well, again, you've got this valve is attached to a little lever here, and at the right time, there's this little weird oblong part of the crank of the gear there that opens it. Okay? So it opens it at the right time where you want to push that out. You've tied it mechanically to when you want that to happen, or on the rotation, right? So here we go. We push out the spent fuel and we draw in more. Now I want to point out that on the intake valve, that's not tied to anything. I don't have a lever or anything. How did that know to open? Just drawing in a vacuum, right? So if this was empty and this is air pressure, that's just going to push it in. It's just going to open the valve naturally. Now, obviously, air pressure filling a vacuum, that's actually something that happens fairly rapidly, but if you have a high-performance car, it's actually not fast enough. Does anyone know what you call it when you actually force the new fuel mixture in there?
Direct injection.
What's that?
Direct injection.
Right, injecting fuel, turbocharging, okay? So that's when you want a car that's such high performance that the natural filling of the vacuum by the outside air pressure can't actually keep up because you're running this so fast, okay? So this is a kind of more, this is not a high performance car. The intake valve just relies on atmospheric pressure to push in the new stuff, okay? So hopefully that gives you an idea of how this actually works. If you just sit here, and this you should have no problems pulling up and having it work. I think it's an animated GIF. You just stare at it for a while and look at all the different pieces, and you can kind of see how the spark plug goes off at the right time. Why does the exhaust open up, the valve open up at the right time, okay? Question?
Yeah, that also would be on a open system as it has exhaust compared to the dynamics would change on a closed loop system. So if that exhaust or line goes right back into the system, that would be a closed loop system, no thermodynamics actually.
Oh, okay, yeah, I mean, I'm definitely not talking about a high performance here. This is probably like a Model T engine or something, right? There's a lot more complicated stuff that goes into this, yeah. So maybe you guys, this is the tip of the iceberg, and if you guys actually go into being, automotive engineers and stuff like that, you'll get a lot of interesting stuff.
Refrigeration systems have closed loop systems. Would be a good idea of a closed loop system would be a refrigeration that's returning refrigerant.
Right, yeah, so the refrigeration is something we're going to talk about a little bit later. The problem with this is that, of course, once you've burned the fuel, you need to have it leave. Yeah, you can't necessarily reuse that. There's nothing left there to reuse. That's why you can't just fill up your tank, gas tank once when you buy your car, and then it just runs forever, right? There's something being expended, right? So at some point, you need to get rid of the exhaust.
Consumed,
yeah.
Consumable.
Yeah, exactly. So, so this is how it works. And again, you can just stare at this for a while and just kind of get a sense of what all the different parts are. So let's go ahead and just calculate. This is all Homework 7 is really about, right? Learning what's the work done, what's the heat flow of all these different kind of processes. So let's go ahead and just knock it out. So let's make ourselves a nice little chart here. Step, what's the step? And of course we have 4 distinct steps of the thermodynamic cycle: A, B, B to C, C to D, and D back to A, okay? And then let's give the name of this step in common engineering parlance. So we said this is called a compression stroke. This is when you put in the ignition. This is where you put in the heat. Then you have your power stroke. And then you have the final stroke where it's the intake stroke together with the exhaust stroke. So those actually fall under the same thermodynamic header, okay? So we might want to also add here, before we start computing heats and works, we might want to add a picture so that you remember what the actual physical thing looks like. So here's just a picture of the piston, or the general situation. I'll leave myself a little room here to do that so that I can fit it. So I'll draw it the same orientation as I showed you, with the piston on the bottom. So the compression stroke looks like this. So we basically compress the gas from its maximum volume of R times V to its minimum volume of V, okay? The ignition is when it is at that minimum volume, the spark plug goes off and lights the gas up. That's your heat input. Your power stroke is when it drives it down. So there's your second stroke, compression, now power. And then the intake exhaust is basically a full trip up and down again. So basically what we approximate is that all that you've accomplished during that is that you've taken what's in the chamber, which is warm smoke, replaced it by cool, fresh stuff. So it is, we've approximated as an isochoric process, okay? So we've gotten rid of the fresh, or get rid of the smoke or exhaust, and then we've taken in these new fresh stuff. But when you've done all that, you wind up with the same amount of volume of gas, but at a lower temperature. So we approximate that as isochoric, okay? So again, if you want to label them, this is adiabatic, this is isochoric, this is adiabatic, and this we approximate as isochoric, okay? The net effect of that anyway. Okay, so let's start putting in heats and works. So this is where you've hopefully gotten comfortable with it on homework 7, so we just knock it out, okay? So for instance, when you have an adiabatic thing, what's the heat flow? 0. This happens much too fast for heat to have a chance to flow to or from the environment. And the work, I gave you a number of different options to choose from last time. I'll just go ahead and use that one. So that's delta T. Of course, what would I use for delta T? It's T final minus T initial, right? So what point do we end at? Well, we ended at B, we started at A, okay? So hopefully I don't have to write this out for every single one. This is TB minus TA, right? That's a B, okay? So what happened to the temperature? Did it increase or decrease? Increased. Okay, what's the sign of the work? So the delta T is positive, but
Negative?
negative. So this is negative overall, right? I guess I'll just put the sign in the corner, right?
Because it's going up.
It's going in, right? We're putting energy into the gas as work, and when work goes in, that's negative. All right? Okay, let's do our other adiabatic process. Same deal. That's 0 heat. And there is some work, of course. What's delta T? Final minus initial, so D minus C. Okay? So what happens when you drop, well, I just gave it away. When I go from C to D, the temperature drops, right? So it's delta T is negative, but the work is positive, right? This is when I get work out. The power stroke is when I get work out. Okay? And again, what's delta T? It'd be D minus C, right? T at point D minus T at point C. Okay, where you finished minus where you ended. Okay, let's go to the other two. Let's go to the ignition. So that's isochoric. How much work is done? 0. There's no area to the curve, right? I'll do that over here too. This is isochoric as well. Okay, how much heat? Well, we just used NC delta T, right? Which C should we be using? This is a gas, so it's a distinction that needs to be made, right? CV, yeah, we're isochoric, so C and CV delta T. Again, you can plug in the relevant delta T's. Do we put heat into the gas or take it out during ignition? In, so it's positive or negative? Positive. Okay? And what's the net effect of expelling warm smoke and taking in cool new fuel air mixture? Is that heat going in or out? It's out, so that'll be negative. Okay. So we've got it. We just calculated everything we might possibly want. So the only really new thing in homework 8 is how to synthesize this information in a different way. Okay? So how might we evaluate the situation? How might we rate the performance of the engine? So let's go ahead and write down the first law of thermo. And I'll think of it in terms of the whole cycle. So in terms of the whole cycle, of course, energy must be conserved. What's delta E for the whole cycle? 0, because somebody else? Is anyone else with me?
Because it's going back to the same position.
Same temperature, exactly. So there's overall, I'm just closing the loop. So the delta T is 0 and the delta E is 0. It's a closed cycle. So that's a common thing with closed loops. And why would you want it to be a closed loop? You want it to repeat it over and over and over again. Okay. So now let's think about Q and W. Well, here's what I'm going to do. I'm going to, for the net work, of course, I would add up these two. And I will actually leave them added up. But for the heat, I want to draw a distinction between heat that went in and heat that went out. Okay? So in this case, I'm going to keep the works together, but I'm going to talk about the heats independently. Okay? So I'm going to dub these two heats, so equals 0. I'm going to talk about them as QH and QL. Okay? Now let me explain that notation that I'm using there. So I'm going to use QH in this case is going to be my Q that goes in. So that's positive. And QL is going to be Q out, which is going to be negative. So what's with the H and with the L? Well, I mentioned, of course, that you have 4 distinct temperatures in this thing, but there are 2 temperature extremes that this thing operates between. The lowest temperature that this thing ever gets to is TA, and the highest it ever gets to is TC. And so I'm going to redub those T low and T high. It's the temperature extremes that the system is operating in between. Okay? And notice here that when heat goes in, this is what gets you up to T high, right? So we said that heat went in from step B, C. So during this step right here, heat was going in to get you up to the highest temperature. That's why I call it QH, because it's the heat inflow that gets you up to the highest temperature that the gas will ever be at. And I'm kind of drawing it goofily as just this big cartoon arrow because there's really no place to actually include this information on a PV graph. But of course, heat does flow in, right, at that stage. Likewise, I'm calling when the heat flows out, I'm calling that Q low because that happens during stage D to A. And in fact, when heat goes out, that is what drops you down to T low. That's what drops you down to the lowest temperature, okay? So here's a way to think about what an engine performance does. So let's say this is a schematic box where this is the engine gas itself. Okay, so this is the engine itself. And how does it interact with its environment? Well, we can think of it as this. You have a T high and a T low reservoir that you're operating in between, right? That sets the extremes of your system. And what happens is that some heat comes into the engine basically, if you want to get something up to T high, you're going to have to connect it to T high, so to speak, right? We're kind of thinking of it as if you want to get something up to a particular temperature, you need to let it come to equilibrium with something that is T high. This is positive, of course, because the heat is flowing in. And then, at other parts of the cycle, we do have that heat flows out. And I'm purposely drawing this as a skinnier arrow, though I don't think I did a very good job. Let me try to make it a little skinnier. So this is Q low, that's negative. And now heat is flowing out. And then, since we kept the works together, we can put the work over here. Here's the net work. And that's going to be positive because, of course, it flows out. Remember, we have an opposite sign convention for Q and for W. So essentially, this is one way to think about the performance of an engine. Okay? What does an engine really do for you? What is it accomplishing? Well, if you, of course, have a high and low temperature, heat would naturally tend to flow from high to low, right? That's what heat does. It flows from a higher temperature difference, or higher temperature, lower temperature. So this is just a completely natural flow. And what we are doing is we are diverting part of that and turning it into useful mechanical work, okay? So essentially, what an engine accomplishes is taking the natural flow of heat from a higher temperature to a lower temperature and diverting part of it to useful mechanical work. Okay? That is what a heat engine or an engine actually accomplishes. Okay? Taking a natural process and diverting part of it to your own ends. Okay? It's like you have a river flowing by your farm and you divert part of that water to irrigation, something like that. Okay? So this gives us a window as to how we might actually evaluate the performance of an engine or really any kind of thermodynamic device. So here's my suggestion. For a rating of how we might judge the performance of it, we'll take what we want to happen divided by what we pay for it. That might be a way that you would rate anything in life, okay? So how good is this, okay? What do you want? Great pizza, okay, big denominator, or big numerator, right? If the pizza is high quality. Okay, well that pizza cost $1,000. Okay, well that's a big denominator. Maybe that pizza isn't so good. Okay, it's not much value. Okay, so this is a rating for how you might rate almost anything. Okay, it's you want more of what you want in the numerator, and of course the cost for what you pay for it in the denominator, that's a negative, so you put it in the denominator, right? Does that make sense? Okay, so let's go ahead and do that here. Let me find some room here. I guess. Let me go over here. So, in the case of an engine, this is called the efficiency. Efficiency, okay?
Efficiency.
So the rating that we use for engines is called efficiency. What do we want this engine to accomplish? We want it to accomplish net work, okay? That's the goal of this thing. We want the car to go, okay? We don't want it to just mess with heat. We want it to do something for us. Well, what do we have to pay for it, of course, is we need some heat flow, right? So we are not going to necessarily get mechanical work for free, right? We're going to have to pay for it by inputting some energy as heat, right? So we gotta put in that fuel, fire that spark plug, that's the cost. So basically that's QH. Does that make sense? So now you guys can calculate the efficiency of an engine, okay? So you guys learn how to compute works. You can add up all the net work that happens during this engine cycle. That's your net work. And then in the denominator, you're not putting in all the heats. You're just putting in the heat that actually flows in. Okay? Now, what is this other thing? This is just waste. This is basically, we can call it exhaust. It does not serve any useful purpose. It's basically the heat flow from higher temperature to lower temperature that we did not actually manage to divert for our own purposes. It just kept on flowing to lower temperature. Okay? So you might say, well, why don't we just use all of it? Right? Why can't we, if 100 joules comes in as heat, why can't we just convert 100 joules to mechanical work? Why would you want to have waste? Well, there's nothing stopping you from doing that as far as we know so far, okay? So the question is, can you get all of the heat to come out as work? So is it possible to have E equals 1 or 100% efficiency? Well, there's nothing to stop you based on the first law of thermodynamics. The first law of thermodynamics is just energy conservation. So it's just gotta, the only thing that the first law of thermodynamics says, so the first law is that the efficiency can't be greater than 1, okay? You can't get more work out than you put in heat. That's just creating energy out of nothing. So the first law of thermodynamics outlaws efficiencies that are greater than 1 or 100%, but it doesn't outlaw efficiencies equal to 1. So that's where the second law of thermodynamics comes in. And I'll give you that in just a moment here. It says that this is not possible, okay? So there is no such thing as an exhaustless engine, okay? I guess I can tell you that right now. I can just write it down. I basically just did, so. The second law of thermo, and there are several different ways to phrase this. This is called the engine statement. This is how the second law of thermodynamics informs the operation of an engine. Okay? So it says that no cyclical process may have as its sole result the conversion of heat into work. In other words, there must have exhaust. Now, I underlined cyclical there because that's really important. If we ran this process from A to B to C to D, and then we just stopped, we wouldn't have this exhaust, right? The exhaust happens from D to A. But here's the problem, is that that's not a repeatable thing, because if you start at A and you finish at D, it's not a process that can be looped over and over again. So this is a cyclical process. So no cyclical process, one that is a closed loop, can have if you close your loop, then there is no way that at some point heat doesn't flow out, and that's your exhaust, that's your waste. Now, obviously I haven't rigorously proved this. I've shown this for a gasoline engine, but you can try it yourself, concoct whatever closed loop you want, and if you close your loop, then at some point you will find that heat is flowing out, and that's your waste, okay? It is impossible to have an exhaustless engine, okay? You must have QL, okay? So one way to think of it is that the first law says you can break even, right? Energy can be conserved. First law, you can break even. The second law says you can only lose, okay? You can only convert part of your energy into what you're looking to do, okay? Does that make sense?
But you're conserving, right? And because the gas exhaust carbon actually is still energy.
Yes,
yeah.
but what we're talking about here is that this is the interesting thing,
what
right?
we need to
So yes, energy is always conserved, but if we're talking about the second law in terms of accomplishing something that you want to accomplish, you cannot ever get 100% of the energy that you put in as heat out as work, okay? So there will be waste that is always occurring, okay? So the first law just says we can't have more energy come out than we go in, and the second law says that you can't even convert all of this heat inflow into work, okay? Does that sort of make sense? Okay, so here we go. Let's talk about the efficiency. I'll give you a couple different options for the efficiency. So the efficiency, it's a value that runs from 0 to a theoretical maximum of 1. We've just said you can't achieve. It's what you want divided by what you pay for it. And then what I want to point out is that I can rephrase this in a way that might be more convenient. Notice that in this expression, there of course will be an energy conservation between the three of these. So I can always solve and find that net work is equal to QH plus QL, or I guess I'll say QL plus QH. So I could put that in here, and what I'd find is an alternative expression for the efficiency using only the heat flows. So QH and QL, okay? Now, you might look at this and say, wait a minute, you just told me that the efficiency has to be less than 1. Or I guess that's another way to put the engine statement. Efficiency has to be less than 1. Except for here, I seem to be directly contradicting that 1 plus something. Of course, what's the resolution? Is this really bigger than 1? No, QL is negative, while QH is positive, so this is less than 1. Some people like to do it like this, just to remind themselves that you are subtracting off of 1, okay? So you can see if the QL can't be 0, then the efficiency will be less than 1, okay?
Makes sense.
So I guess let's see how far we can get in calculating the efficiency of this particular engine. So I have my QH and QL, so I'll just throw them in. So this is my efficiency of the Otto cycle. So 1, I'll just use 1 plus, and then I'll put in my, make sure I put in these correctly. So the QL, the delta T that's relevant for that, that's stage DA. So I have to take final minus initial. Finish at A, started at D, and then over here, that was the ignition stroke where I put the heat in. So I finished at C, having started from B. So right there, there's my efficiency. It doesn't look like much yet, but let's go ahead and simplify. Now those temperatures are related, and I can, if you're wondering what I can do with the adiabatic processes, let's go ahead and take a look at those. I'm going to have to clear some space. So the adiabatic processes, the compression stroke and the power stroke, I can use my identity, right? So we learned last lecture that TV to the gamma minus 1 is a conserved quantity. So let's do it. So TAVA to the gamma minus 1 is equal to TB VB. Same thing. Is that okay? Now the volume, VA, is RV, and the volume at B I just call V. Remember, that was the way that I characterized those temperature extremes. So this tells me, if I cancel off the common stuff, that temperatures A and B are related in this way. Yada, 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 same idea over here on the power stroke. This will be TC, and this will be TD. The only difference is that the R term is on the other side, because now I'm going to higher volume, and so higher volume is the final. So again, if I did this a little bit quickly, I'm leaving steps that I think you should be able to fill in when you try it yourself. Rewrite your lecture notes before the next class, which you guys all do, right?
Yeah.
Okay, great. Okay, so so let's work out what I have. See if I can finish this before the end of class here. So what I'm going to do here is I'm going to choose to keep A and D as the temperatures, and then I'm going to substitute in for C and B in terms of those two. So let's go ahead and do it. So my efficiency is equal to 1 plus, and for reasons that will become apparent in the next step, I'm going to reverse the subtraction order in the numerator, and then obviously in order to do that I need to pull out a minus. And then over here for TC, I'm going to plug in this TDR to the gamma minus 1, and then for the other one I'm going to plug in like this. So hopefully you can see where I'm going with this. I put them all on a common temperature platform specifically, so when I factor the R to the gamma minus 1 out of that, hey, check that out, that's cool. So this cancels with this. And now I have found what is the efficiency of my cycle. And it turns out that it depends only on the compression ratio and type of gas I use. So gamma. Okay. Now, that is one way to express it. This is the efficiency of the Otto cycle. But I do want to point out there are several other options. R to the gamma minus 1 can also be expressed in terms of the ratio of these two temperatures. So alternate ways to think about it would be, let's maybe make sure to get these right. So this would be 1 minus TA over TB, or similarly I could express it as 1 minus TD over TC, right? Those other forms are less clear at this point why they might be interesting, but I do want to have them there for later reference. And I do want to point out that this is T low here. So this can be thought of as a ratio of the lowest temperature with one of the intermediate temperatures. And then over here, Tc is my highest temperature. So I can think of it also as a ratio of 1 minus, and then one of the intermediate temperatures divided by the highest temperature. So that right there, it's unclear why that's important right now, but we'll find out on Monday. Okay, so let's knock off there for today.